Since we can pick a 0 and a pole for our controller, we have some design choices that we can make. So let's go through a couple different designs, and we'll see how our choice of 0 and pole is going to impact the behavior of our system, as well as the input it takes to get control. So in all cases, this equation is still true. We need to pick the pole and the 0 such that this equation is satisfied. So we could either pick a pole and find a 0 that makes it negative 45 degrees, or we could pick the 0 and then find the pole that makes this equation true. So the designs we're going to go through, I'm going to arbitrarily be choosing values of zeros, finding the pole, and seeing what the behavior is. There's not a specific systematic method I'm going to be using in the designs. So for the first design, I'm going to just choose that the 0 for the compensator is going to be 2. So I can put 2 in for ZC. Now, that second angle I'm able to solve for as a number. It comes out to negative 90 degrees. I can move that negative 90 over to the other side, which is going to give me 45, and then I can multiply through by the negative. That's why the right-hand side is still negative 45 degrees. And now I have one equation for one unknown. The angle by definition is going to be that 4-quadrant arctangent. I put the negative 2, the imaginary part, on top, and then the denominator is the negative 2, the real part, negative 2 plus PC. So solving this, I can take the tangent of both sides, and this tells me that if I choose the 0 to be 2, then the pole in the compensator has to be 4, and that will satisfy that top equation that the sum of those angles is negative 45 degrees, and then the sum of all 4 angles is 180 degrees, which ensures that negative 2 plus or minus 2j will appear on the root locus. So with the 0 chosen and the pole chosen, I can put together my G' or my GRL, and this is what I want to put into my root locus equation. So now the top from that 0, I have an s plus 2, and then I have an s plus 4 on the bottom. Now, it turns out that in this case, by choosing a 0 in my controller to be equal to 2, that actually one of my open loop poles from the plant cancels with it. See, I have an s plus 2 and s on the top and on the bottom. So effectively, my G' is now down to 1 over s times s plus 4. We'll see actually what benefit of this was by choosing a 0 that was also one of my open loop poles. So now I can take this G' and go into MATLAB and make my root locus. I'll be using the same bit of code to do all 3 of my designs. Right now I'm only looking at design number 1. So in 16, I am just demonstrating now design 1, but the same thing will be run each time as I go through the second and the third design choice, and if I made any others I wanted to. Okay, so let's make the root locus for this design choice. And this is what it comes out with. We have the poles we can choose in blue and in red. So again, we want our dominant poles to be located at negative 2 plus or minus 2j. So let's get pretty close to it. All right, so to get a pole in the closed loop transfer function of negative 2 plus or minus 2j, I just have to select the plus here. It's the same for both. This is saying I will need to use a gain of 8. Right? I can select all these other closed loop poles, but I selected the minus 2 plus or minus 2j for a reason. So all I need to use my root locus for is to find how much gain it takes to get to that pole. And recreating it here on the slide. So that means that my closed loop transfer function is going to be, this is always true for the systems we're going to look at where we're ignoring the sensor, we're ignoring the actuator, that it's going to be kg' over 1 plus kg'. G' we established on the previous step where we chose the pole and the 0 for the compensator, and now k we just found to be 8. So if we go through the algebra here, do the expansion, we get that the closed loop transfer function is 8 over s plus 2 plus or minus 2j. I didn't expand the denominator here. It is quadratic with an s squared, because what I want to look at is what are the dominant poles, really all the poles and the zeros of the closed loop system. And we see here actually that we have no extra zeros and we have exactly 2 poles. So by choosing a 0 in the compensator that was the same as an open loop pole, we actually get a closed loop transfer function that is a pure second order system. So when we go into the simulation, the theory and the simulation should match exactly because we don't have an extra zero or a third pole coming through and affecting the baseline system. The true system is the baseline system for this controller. So we know how in theory it's going to behave already from the previous lecture. So let's look at the simulation and just see how does it actually behave, at least in simulation numerically. So I have built the Simulink model here. The gain block is going to be first, then my controller. I will build this controller as just a transfer function with the Z1 and P1 as the zero and pole for my design. And that's going to change for design 1 versus the following 2 designs. I am just for the sake of continuity using a limiter here. Because we don't have a derivative controller, we shouldn't see a giant spike or a giant kick in that input effort like we saw for the PD controller, but I'm leaving it here just to more realistically simulate the maximum we could put into a system. Now I do have it pretty high here, I just have it set to 100. We're not going to see it come into effect, but I can put that up or down based on real world conditions. And then that same plant. All right, so the controller is built, and this is robust for all 3 designs, so I don't need to change anything in here because in MATLAB, I'm going to be changing the K, the Z1, and the P1 value. And that's what's happening up here in the if block. Since I already did this problem, I just have them set all up here at the beginning. So we're using a gain of 8 from the root locus, a 0 of 2 that we chose arbitrarily, and a pole of 4 that we found by having all of the angles of G prime equal 180 degrees. All right, so now I'm going to run this simulation and I'm going to plot the results. I have here, it's finding the overshoot, it's finding my peak time, and it's going to find the maximum input effort. Again, something that we are typically interested in finding. So I'll just run this whole section now. All right, so we see graphically what the response is of the output voltage. It comes up to some peak. I'll just let MATLAB figure out what that value is. And then it comes down and it's going to be steady at 5 volts. So the first thing the controller is supposed to do, does it drive the output to that constant 5 value, which is to say, does it drive the error to 0? Yes. So it does do the first job that it really has to do, drive the error to 0. We see here graphically that it requires a maximum input effort of 40. If it's an electrical system, that would be a 40 volt peak. Maybe that's too much. We'll have to investigate that separately. And we see it does behave like the second order system. We have this overshoot, and then it comes down and settles to our steady state value. So I have MATLAB automatically computing this. So our overshoot, we're getting 4.3%. This is coming out of Simulink. We're seeing a peak time of 1.57 seconds. And for this controller, the maximum input effort is 40. So we'll put this one aside. We're going to compare all of our designs at the end, but this one did what it was supposed to, and we knew that it was going to act like a second order system because the closed loop system was purely second order.